All right, let's get into it. Today, we're basically going on a safari, but not to the savannah. We're headed to the deepest, weirdest corners of the cosmos. We're going to go hunting for cosmic monsters, stars so extreme, so out there that they make black holes look kind of tame. You know, we're all pretty familiar with the usual suspects up there. But what if they're just the tip of the iceberg? What if the universe is hiding things that are way, way stranger? Well, that's exactly what we're going to explore. So, here's the game plan for our little trip. We're going to start with what we know, then climb a ladder of increasing strangeness. We'll meet some of the top contenders in this cosmic zoo, and then we'll get into why looking for these things is one of the most exciting frontiers in all of science. Okay, so before we dive into the truly bizarre, we need a baseline, right? Let's just quickly touch base with the stars we actually know and can see, the ones that, play by the normal rules of physics. So you've got stars like our sun, happily fusing hydrogen. And then you have what's left over when they die, the stellar corpses. White dwarfs are held up because electrons just refuse to get any closer to each other. It's like quantum social distancing. And then there are neutron stars, where gravity is so insane it mashes protons and electrons together into one giant ball of neutrons. These are pretty much the limits of standard physics. But what happens if you push even harder? To keep all this weirdness straight, physicists had this cool idea called the stellar exoticity scale. The best way to think about it is like a ladder. Every rung we climb takes us one step further from what we've actually seen and deeper into the wild possibilities the universe might be hiding. And this scale really lays out our whole journey. See, each step up this ladder means we have to assume some new, unproven piece of physics is actually real. We go from new states of matter to entirely new particles, all the way up to brand new theories of gravity. So let's start climbing. Our first stop on this ladder, step 2, is all about a new state of matter. What we do is we take the densest thing we know exists, a neutron star, and we ask a really simple question. What happens if you just squeeze it even harder? Well, if our theories are right, you get a quark star. We're talking about an object maybe the size of a city, but it's so incredibly dense that the neutrons themselves literally break down and dissolve into a soup of their fundamental building blocks, quarks. Now here's the really important part. These things are totally plausible. And if we ever actually find one, it would be a natural laboratory for studying matter under conditions so extreme, so intense, that we could never, ever hope to create them here on Earth. It would be the ultimate test for particle physics. This gives you a perfect visual of the transformation. It's really just a question of pressure. You start with a ball of neutrons, all packed in there shoulder to shoulder. Then you crank up the gravity so high that they just melt, losing their individual identities and becoming this single unified object made of pure quark soup. Okay, time to climb up to the next rung. Here things get even weirder, because we're not just rearranging particles we know about, we're talking about stars made from particles that might not even be in our standard model. What if a star wasn't powered by a nuclear furnace, but by something else? I want you to meet the dark star. And don't let that name fool you. These things wouldn't be dark at all. In fact, they could have been absolutely colossal, puffy, incredibly bright giants, just glowing away at the very dawn of the universe. And here's where this wild idea gets really exciting. This isn't just theory anymore. Astronomers using the James Webb Space Telescope have found a few objects way back in the early universe that fit the description of a dark star almost perfectly. We might literally be looking at the ghosts of these dark matter-powered giants right now. So the whole engine is completely different. Our sun works by smashing protons together. A dark star, on the other hand, would have collected a huge, dense clump of dark matter at its core, and those particles would just crash into each other and annihilate, releasing a steady flow of energy. All right, let's head for the summit. We're going to the very top of the ladder now. This is the rung where we're not just adding new particles, we're actually questioning the nature of gravity itself and asking a pretty radical question. What if black holes aren't really the end of the story? So, say hello to the gravistar. The idea is mind-bending. It suggests that just like water can freeze into ice, maybe collapsing matter hits a point where it undergoes a kind of phase transition just before it can form a true black hole. It would form a super dense shell around a core made of, well, the weird energy of empty space. This is a really profound concept. From the outside, a gravastar would look and act almost exactly like a black hole. It would bend light, it would pull stuff in, but, and this is the huge part, it would have no singularity and no event horizon. And that one little difference could solve some of the deepest, most frustrating problems in all of physics, like the whole information paradox. So, quark stars, dark stars, gravastars, we've got this entire zoo of theoretical creatures. But why do we even bother looking for them? What's the point? Well, the answer is actually pretty simple. Finding just one of them would completely change our understanding of reality. What's so cool is that all of our biggest, most ambitious ideas about the universe, the big theories of everything, they each predict their own unique set of these exotic stars. For example, string theory and ideas like supersymmetry, or SUSY, they predict things like boson stars. But a competing idea called loop quantum gravity, it predicts something totally different, like a Planck Star. This chart basically shows you which theory is betting on which horse. And that right there, that's the ultimate prize. These objects aren't just weird things floating in space. They are the battleground where our deepest, most fundamental theories about the universe will either win or be proven wrong. Finding one isn't just an observation, it's an experiment on the very fabric of reality. This quote just nails it, doesn't it? The universe doesn't really care what we think is normal or easy to imagine. The universe is only bound by the laws of physics, and it turns out those laws allow for some absolutely astonishing, bizarre, and wonderful possibilities. Our job is just to get clever enough to go out and find them. So the hunt is on, for real. With new amazing tools like the James Webb Space Telescope and gravitational wave detectors, we are absolutely in a golden age of cosmic discovery. And the first confirmed find won't just be a new entry in our cosmic zoo, it's going to point the way toward a whole new understanding of everything. Thanks for joining me on this tour.